So hello YouTube. We got some fun stuff in today's lecture. This lecture is called Functions Are Data, which they are. So we're used to programs that juggle numbers around and that juggle bits around, and some of those programs we think are the functions we write. But guess what? It's perfectly reasonable to write functions which juggle other functions around. And we are going to spend some time doing that. Um, so to do that stuff, I'm gonna need a new data structure. By the way, can I just check, is the font okay at the back? Cool. We're gonna need this data structure, which is the data type of lists. And there's something new to see here. Let me, I have a convenient pointing device. Yes, or Clemens. Yes, right. So we haven't seen one of these things before, right? You know that in ask, if something begins with a lowercase letter, it's a variable. It stands for something else. And what we're saying here is that we are inventing not one list type, but a whole bunch of list types parameterized by this variable x. And this x is going to give the type of the things in the list. Because, you know, one day we might want a list of numbers. The next day we might want a list of bits. We might even want a list of lists. So that's the idea. So there's two ways to make a list. You can make nil, which is the very short list that's got nothing in it, hence the name. And you've got this colon symbol, which is pronounced cons, and that's short for construct. It was stolen from a language that was invented in the 1950s. The language was called Lisp, and it put things together into list shapes by gluing together one element to the left of the colon and then the whole rest of the list to the right of the colon. So we're building up lists one thing at a time with the left end nearest to us. And my father was a really enthusiastic Lisp programmer, and I rather suspect I was named after the cons operator. That's the sort of thing he'd do. I mean, quite apart from giving me a Catholic name to get me beaten up. He was a Johnny Cash fan as well. Well, I know. We'll do a Northern Irish version of A Boy Named Sue. You know. So that's one reason why I'm keeping my name, actually, because it's been transgressive my entire life. It's just now a bit more so. Anyway, we got lists, and the plan is to write a function list out, which takes as input some function from numbers to numbers, and we're going to make a list of the first however many outputs of that function. So if I say, so this number is going to say how many outputs we would like. This computes a whole infinite sequence if we want it to, but we just want the first however many, and we want to get them back in a list. Okay, so let's get started. So I'm going to work inductively on n, so I'm going to count out the number of elements I have to generate. So I go inductively n. And accept from n. Accept. Okay, so this is the easy case. Our customer has asked for 0 elements of the sequence of outputs from f. So that's very easy for us. We don't have to do very much work. We just say that'll be nil then. Okay, fine. Now, this time our customer does want at least one element coming out from F. So we know how to start. The first output of F will be given if we send 0 into F. That's going to be the first thing in the sequence, F of 0. And then I put my cons operator to say, and after this comes the rest of the list. And now, here's the tricky bit. Well, I want to say, list out something n. X, yes, quite right. Yeah, X, right. I'm working inductively. I'm counting down this number. But the trouble is, if I just say F here, I'll get another copy of F of 0 next time round. I'll just get the first element of the sequence over and over again. So I need some way to move the function along. I need to think, right, what function generates the sequence starting from 0 where F starts from 1? You see this thing like that already. Remember, for formula, we defined shift to replace the input by 1 plus the input. Let's do the same thing here. So I'm going to define shift fun for functions. So shift fun f at n is going to be f of the successor of n. So shift fun f of 0 is f of 1. Shift fun f of 1 is f of 2, and so on. So now if I send in shift fun to the recursive call, then the rest of the list will start from f of 1. Oh, what have I done? I haven't defined shift fun. I have to say define. It's too easy to write Haskell instead of ask. Right. Okay. So that's a lot of stuff. Sometimes it's nice to run programs. Actually, I'm going to just do a thing. I like 5 today. Yeah. Such a big number that it's worth giving a small name. I could use 6 and that's a larger number with a smaller name. But 5 it is. And then what I'm going to do is I'm going to test list out, and I'm going to get my function by evaluating a formula. Let's pick evaluate x. And let's have the first 5 outputs from evaluate x. And if we see what's come back, I'll just make the list nice and vertical for you. We've got 0, 1, 2, 3, 4, and that's the first 5 elements, and then nil. Okay? So you see what happened there? We fed in evaluate x, right? So remember, evaluate takes a formula and then a number, and it uses the number to give the value of the variable. But that's the same thing as saying evaluate takes a formula and it gives you back a function from numbers to numbers. And that's the function we're listing out. So we're giving out this list of x when x is 0, x when x is 1, x when x is 2, and so on. See what's happening? And all the way along, we actually, instead of moving the input to the function, we moved the function and kept applying it at 0. But we moved it in a way that had the same effect as counting up on the input. Okay, let's have another one. Let's evaluate x squared. What have I done? I didn't close my parenthesis. So I've hit accept. Now I'll just again tidy. We've got 0, 1, 4, 9, and I promise you that's 16. And so on. So we're making the list of all the squares. So that's cool. We've got something where you plug in you send in a function, and our list out uses that function several times over to produce a sequence of values. And this sort of stuff is kind of straightforward to do in functional programming languages. They're called functional programming languages because they chuck functions around. And for some reason, it took Java a long time to get wise to the idea of also chucking functions around. But they've got there. But anyway, that's list out. It makes lists from functions that generate sequences. So.
Indeed, but so there's one thing about the list out which is still a bit peculiar at this stage, and which happens very often if you write this kind of programs, because we were just thinking about functions on numbers.
Get
right?
the other room, Mike.
We were just thinking about functions on numbers so far in this whole discussion. But if we go back to the definition of list out here, so it takes a function from numbers to numbers and gives you a list of numbers here. But in order for this function to make sense, we take the list out function, the output type of the function you apply list out to doesn't really matter. So the function that you feed into list out, in the whole discussion, it doesn't matter that you get a number out here.
Yeah.
And you get a list of numbers.
Not all sequences are sequences of numbers. So yeah, so you want to...
So ideally, we want to use this feature that we've just seen in the definition of list in a way that we can use type variables. We can use type variables also when we specify the type of a function. So rather than saying we take a function from number to number, we just say we take a function that gets a number as an input, but outputs something. And that's something, I don't know, you want an A or you want an X?
Let's have an X.
Okay, let's have an X. Important is that it's a lowercase number, but otherwise we're fairly free to choose. And then if you have a function from number to X, then if you apply list out to it, it takes that list of outputs, and each of the outputs will be of type X. So therefore you get a list.
Yeah, and you'll need to fix up shift fun as well.
Oh my God, I need this. Okay.
Right.
Indeed.
So it's only important that the input to the function is numbers, because we're making a sequence. The output could be any old thing. So as long as we remember the same...
We lost somebody, sorry.
Yes.
So anyway, we can now also... wait a second. Now where am I? need to go up here. We also need to fix the output function here. So it's from shift fun, takes a function from f to x and gives you number to x and number to x.
Right. Yep.
Is this all right now?
I think so. Let's hit send.
Thanks for doing the scrolling because it would definitely go the
Yeah.
wrong way around.
Right. And you see the program is still completely fine. And we're still, the examples are still working. So what happened here? Right. You should think of this X in the type as standing for not so much, well, if you're the caller of the function, it stands for anything you like. If you're trying to write the function, it stands for anything the devil likes, right? The person who uses list out is going to choose what sort of things we want in the list. So the person who writes list out has to put up with anything. But actually, that's really cool because this type X could be anything, we know almost nothing about it. The only thing we know about the type X is that we have this function, which means that we know that everything that comes out in the list must have come out of the function. Whereas when the type was number to number, we could have done all sorts of things because we know about all sorts of numbers. We didn't have to use the function at all. I mean, in terms of what program would have type checked. So it's actually, although sometimes it's a bit strange to have variables standing for things you don't know and unknowns make you worried, what you need to learn is that the less you know about a type, the fewer choices you need to make about how to make use of it. You know, less is more when you're confined like that. You have fewer decisions. But let's just check. I thought let's do test list out even 5, and I'll hit send, and you can see what's come back is true, false, true, false, true, because 0's even, 1's odd, 2's even, 3's odd, 4's even. So we put in a function that spits out bits, we get a list of bits. Right. Now we can even feed the thing to itself. And if I accept, you'll see what comes back is nil, then 0 nil, then 0 1 nil, then 0 1 2 nil, then 0 1 2 3 nil, and that's the end of our list of lists. You see, that's the result of calling list out on evaluate X for the first 5 numbers. So these things, you can even feed them into themselves. So the outer list out is operating at the type list of number, and the inner list out is operating at the type number. So we're using our freedom to choose whatever X is in 2 different ways in one go, which is kind of fun. Okay, let's see if we can do something else. Mucking about with functions. Yes. So we've been using evaluate for formula, but I said that we've been looking at evaluate as taking a formula and a number and giving us back a number. What I'm going to do now is just rearrange evaluate a little bit to take only the formula and to output the function. So I'm going to comment out the old definition, which will make the later boxes go crazy, but I won't look until I'm done. Yes, but I want to replace the old one.
Okay.
So yeah, so here you notice I'm just giving P.
Type stays the same. Though.
Type stays the same.
Because there's some invisible brackets anyway.
Yes. The type could just as well be written like that. Arrow groups to the right. So now you can see I've only got the formula. Okay. So let's figure out. If I get the variable, I need to give back the right function. And the variable stands for, or encodes up, the function whose output is exactly its input. So I can define that. That's got a popular name. It's called the identity function. Having an identity crisis.
Can you mix?
Okay. So you see, I've defined a function which doesn't care what type it works on. Whatever type it accepts as input, it gives the same type back as output. And that's because its output is exactly its input. We can use the identity function at any type we like. And I've said that we interpret x as the identity function for numbers. Okay? Next, for numerical constants, we need a way of making a function which ignores its input and always gives back the same output. So that's a very boring function, but it's sometimes important. That function is called constant. And because I am old-fashioned, I'm going to spell it in German. Yes. So so you give it the x we want it always to return, and then no matter what a we feed in, out comes x. So this is a function whose first input says what it's going to give back always, and then its second input is the thing that gets ignored. So I'm going to say here, this is constant C. Old-fashioned people abbreviate constant to just K. But I'm spelling it out.
I hope it's clear that the two x's are very different, for example.
Yes.
Constant, because one is a type variable.
One is a type variable and the other is an element. But I choose to use the same letter in the type to talk about element types and in the program to talk about element values, because I want to remind myself that the variable x is standing for a value of type x. So I'm choosing to use the same name deliberately to remind me what's what. Okay. So then to do the other two cases, I'm going to build a gadget which I call pointwise. And this takes an operator that takes two x's and gives you back an x. So something like plus or times or whatever, if x was a number. And lifts it to work on functions that produce x as an output. So a to x to a to x to a to x. What a lovely long type. I'm going to put a new line in here. So pointwise takes our operator, that's our x to x to x, and then f and g, which are both functions from a to x, whatever a might be, and then it takes an element of a. And what does it do? We apply f to a, we apply g to a, that gives us individual values of type x, and then we combine those values of type x with op. So I'm going to hit send on that. Everything's cool. And now I say that to evaluate q plus r, you do pointwise plus on evaluate q and evaluate r. And it's going to be the same stuff for pointwise times evaluate q, evaluate r. Right? So the pointwise captures the recipe, feed the same input to both functions, and then combine the outputs. That was the recipe we used in our old program, and now pointwise actually gives that recipe a name. So I hit send, evaluate is defined, and if I scroll back down, you'll see all our examples are still working. Isn't that such a relief? Yes. So that's one thing that functional programs are good at doing. Because functions are just data and can be juggled around and plugged together, we can write functional programs that capture as single definitions patterns of programming. So here we captured the pattern, feed the same input to both functions, then combine the two outputs. And it doesn't matter what type we use it on. In this case, in our example use of pointwise, a and x both turn out to be numbers. But you can do pointwise on any sort of operator as long that takes two inputs and one output, gives one output of the same type. So that's a useful piece of kit. And again, the fact that the type is so abstract means that you know some pretty strong stuff, right? You know that you have only two ways to manufacture something of type X in the first place, namely these two functions, because that's all you know about the type X. So there are way fewer ways to put this jigsaw together, right? It's like what's happened is that that someone's given you a Lego kit where the knobs and the holes are a funny shape, and there are like way fewer models you can build because you can't just plug standard bits of Lego into the funny holes. So you got the abstraction is actually working quite hard for you. Okay, we were worried we might underrun, but we've got a plan for what happens if we do underrun. One more gadget. Oop. Now, what have I done? One more gadget that we're going to cook up is this piece of equipment that we'll be using a bit in the next few weeks. It's called Some Fun Below. And the idea here is that instead of listing the first n outputs of some function f, we want to add them up. So we want all the outputs of f for inputs below n. We'll have examples in a moment, but let's get there. Fortunately for us, adding is commutative, so we don't have to add them up in the order f of 0, f of 1, f of 2, the way we built the list in list out. We can add them downwards. We can count down and add them up and we'll get the same sum. So that at least is some help. Right. So if I add up the outputs of F for all the numbers below 0, well, that's all none of the numbers below 0. Yes. So I'm adding up no things. What total do I get when I add up no things? 0, the neutral element of adding. So much of computer science is about figuring out the right way to do nothing. And, you know, 0 is the right way to do nothing when you're adding stuff up. Okay, otherwise, we've got some work to do. There are numbers below successor of x, and one of those numbers is x. And then we need to add up the rest of the numbers that are even smaller. That's to say, the numbers which are strictly below x. So we make a recursive call. Okay. So let's have a test of that. Sum fun below the identity function and 5. You knew that was coming, didn't you? So this should be the identity function applied to 4, then 3, then 2, then 1, then 0, all added up. And sure enough, that's, what is it? It's 10. So this turns, so sum fun below turns the identity function into the function that computes the triangle numbers. If I say test sum fun below, thin below, sum fun below, and then I say evaluate x times, so x plus x plus the constant 1. So I'm adding up the odd numbers below 5. I'm adding up 1, 3, 5, 7, 9. Then what comes out is quite a big number, which I hope you can see is in fact 25. That's 5 squared. And of course, we can put these things together. So that now we've got our sequence, which is 0, 1, 4, 9, 16. So that's to say, if we do the sum fun belows of the odd numbers, so 2x plus 1, we get the square numbers. Have you noticed that when we started with a linear formula and did sum fun below, we got something which grows quadratically. So there's something going on there about how sum fun below relates to the notion of degree that we've been exploring. I mean, likewise, if you do some fun below for a constant function, you'll get something linear. Let's just check that. So test, list out some fun below, constant, let's say 2. Is that enough brackets? No, that's enough brackets. And let's have the first 5. What comes back? Just tabulate them. 0, 2, 4, 6, 8. Very Tom Robinson. That's yeah, so we're adding up copies of 2 and we're getting the even numbers. So again, we put in something of degree 1, out comes something that's so put in something that's degree 0, a non-zero constant, and out comes something of degree 1, right? 2x. It's linear. Okay. Let's also just check if I choose, this may seem silly, but it's worth a look. If I choose to list out the outputs produced by the constant function returning 0, I just get a load of zeros. So that's to say, doing some fun below to constant 0 still gives you constant 0. This is one reason why we like, that's the reason. Actually, this is the key reason why we like the degree of the constant 0 to be minus infinity. So we can say some fun below increments degree, but if you increment minus infinity, you still don't escape from minus infinity. So, no amount of furious addition will turn a load of zeros into anything else. Is kind of the point. So that's fun stuff. And it's going to show up. I'll just have a quick peek at that's me being a fool. I'll fix that straight after this lecture. Last year's material spelt plus PLUS. Nobody could read anything. I think it's nicer to write our usual plus symbol in fix. So I need to fix this up. But yeah, the same thing happens with this definition. So this is what happens when I build stuff at 6 o'clock in the morning. Right. So you're going to get this rather special function, which we're going to talk about on Monday, called choose. And you're going to show some useful properties of it. So in particular, things, so choose takes 2 inputs, which I'll call N and M. And it tells you how many ways there are to choose N things when there are M things available. So, for example, if there are N things available and you have to choose one of them, then there are N possibilities. Shocking stuff. Did you ever see a thing at school which might have been called the binomial theorem? Does that ring any bells? Doesn't have to. Like if you've got x plus y all to the n, and you multiply that out, you get a big long collection of terms, starting with an x to the n, and finishing with a y to the n. And in the middle, there'll be some terms that are a jumble of x's and y's, and they will have different coefficients. And those coefficients are the things computed by choose. And you may also have seen funky formulae for this involving factorials. Does that ring any bells? I mean, this is just me by way of saying I'm not going to go anywhere near that factorial definition of choose. I'm going to keep it simple, and I'm going to make use of a fabulous and marvelous invention called Pascal's triangle. Have you seen Pascal's triangle? Does that ring any bells? Well, we shall be spending a little bit of time exploring fun and games with Pascal's triangle, and there will turn out to be a wonderful relationship between the choose function and the sum fun below operator that we've just built in this lecture. So that's where we're going. Oh, yeah. Also, here's another little teaser for you. Have you noticed that that sum fun below, right? The thing that you have to add to sum fun below f of x to get sum fun below for the next number up is f of x itself. So that's to say, the forward difference of sum fun below f is exactly f. In other words, what we've just looked at today shows us that sum fun below is the appropriate notion of integration, which corresponds to the forward difference as our differential operator. Sum fun below does diff backwards. So these pieces that we've been studying do all fit together. It's a massive conspiracy, and we're gonna get there. I think I'm going to, if I can find the meeting controls, I'm gonna stop. Oh, there we go. I'm going to say cheerio, YouTube.